Okay, welcome to this lecture number 4 of week 1 on the course of control engineering. So far we talked about systems, we understood a little bit of their transient versus the steady state behavior. We talked of evolution of the system. We also looked at how a process responds to inputs, in which we classified things as static versus dynamic, linear versus non-linear, and so on. While we were understanding static systems or static versus dynamic, in the conclusion we said something here, right? These are like time independent. Okay, time independent essentially would mean that the evolution is instantaneous. And here the evolution is not instantaneous, it evolves with time. Okay, that is one classification of how we look at static versus dynamic in terms of their dependence on time. Okay, we'll go further into our classifications and see what lies next. Now, suppose I maybe start with my fan itself, right, or an air conditioner. Or even I buy a new laptop, I switch it on, it just boots instantaneously, or well, almost instantaneously, right? I think in maybe 30 seconds I could log in and so on. The fan also responds to my input quickly, and if I switch on the same fan maybe 5, 7, 9 years later, you see that it kind of takes a little time to achieve its steady state speed. The response is slower, it's a little less efficient, it makes maybe a little bit more of noise, and so on. What happens in this case is that the system performance it changes over time, and in many cases deteriorates with time. And in the case of a fan or a laptop, it just turns out or even a bulb, right, which was very nice that it gave me output as soon as I switched on the input. But if you see over time, the amount of light or its intensity reduces, and ultimately before it dies, and you buy a new bulb, you see that your room is more illuminated and so on. So the performance is deteriorates with time, and it also has, I can say, reduced efficiency. And many systems around us we see are the systems which evolve with time, right? During peak hours, your cab demand might be a lot, your people accessing metros or local trains might be a lot, power demand during summers, commodity demand during festive season and all. There are things which kind of vary, or even the intensity of sun from say morning 6 a.m. when it rises till 6 p.m. or so, something like that when it sets. Things evolve with time, right? And also maybe our clothing pattern evolves with time, and so on. Okay. Also look at know how many people would have COVID fresh in their minds. A lot talk about people being people being in contact with infected people. Let's say and the chances when you are in contact with infected people are much higher, and until you are infected, everyone is vulnerable, and we call them as susceptible people. Let's say there is a infected person here. I call this person X, person Y and Z. They talk to each other without really coming into contact with person X. Now, person X comes in contact, say at time t equal to 2. This could be the day 1. This could be the day 2. Okay. So say suppose this sequence of event happens, and if I look at, okay, I say look, I see what happened in the last 2 days. I said these 3 people talk to each other, and therefore all of them can be, there is a possibility of both Y and Z to be infected. You see the distinction here, right? If I just say how did these 3 people talk in the last 2 days, they say, okay, Y talk to Z, X talk to Z, and therefore by transitive property I would say, well, they had come in contact with each other. Whereas if I look at and if I just look at over 2 days, I would say, well, there is an equal chance that Y and Z will get infected. Whereas if I look at what happened on day 1 and day 2, look at the time evolution of the contact, you see that okay, the Y came in contact with Z before X came in contact with Y. So if I look at it as things which are depending on both on how X, Y and Z talk over 2 days, not over the entire 2 days, then the only possibility is of Y getting infected, because Z came into contact with Y before Y was infected. Okay. Now, if I now look at the output measured as how many people are infected given that X is infected, the output of the system is dependent on the time at which I am measuring this, right. So, and therefore, there are some experiments or some phenomena which depend on what time the experiment was done or what time the input was applied. We also see this because the system parameters, you know, your mass, resistance, and maybe if I go back to the example of a fan, it slows down because maybe the bearings are not maybe lubricated enough, the friction increases and so on. And many of these parameters like our own mass changes with time, or my agility at when I was 20 is not the same when I was 40 and will not be the same when I am 60 or 80, right. Things change with. So, system parameters will change with time. So, if I say V equal to IR, I assume that the resistance is the same all the time, and therefore the response will also be the same. Whereas if R will change with time, say it is 100 ohms when I buy, then maybe it becomes 101 after 1 year and so on, you will see a different behavior in the output. Okay. However, okay, in our experiments or analysis, most of the time we will assume that the parameters don't change much from morning till evening, and therefore whenever you buy some equipment, they kind of give you the tolerance bands in terms of the operating conditions of voltage, temperature and so on. Okay, but still it gives us something nice to study. These are time varying systems. So, the amount of current that this R gives depends on if you are doing this experiment now or doing it at say 10 years later. Okay. So, okay, how do we write this mathematically, right? So, the output of a system y of t for an input x of t will be some function. Now, I do not really classify this as any linear or non-linear, it could be whatever, because we understand static dynamic, we also understand linear and non-linear. So, this could be whatever. Okay. So, if the output of the system, if the input is delayed by delta, so I will get some output, right. So, the input when I say delayed, I am not doing the experiment now, but I will do the experiment 1 year later, and I say, well, this is the 1 year later, delta here is say 1 year. This will give me a certain new output which is y t, also depending on delta, which will be f of x of t. Now, x of t is now replaced with x at delta. So, the input comes 1 year later or delta times later. So, I will call this as y prime t. Okay. Now, suppose if I just take the output and delay it by some delta time. Okay, and I call this as y of t at t equal to t minus delta. Now, I compare these things, right, the output when the input is delayed and the output when the output by itself is delayed. So, when the output y prime t with a delayed input is equal to the output by itself delayed by delta seconds, the system is called time invariant, and if it is not, then the system is time varying. Okay, if the mathematics is confusing, let us see this one, right. So, I have an input, it goes through a system and gives me output. Okay, and I say I measure the output say 1 year later with some delay, it gives me a certain output y of t minus delta. Okay, now what do? Is I put this delay here, I delay the input by 1 year. Now, I measured the output because of the delay in the input. If these two agree, then the system is called time invariant. If these two do not agree, the system is called time varying. Okay, I am assuming that this classification is clear here. Okay, so let's see with some examples of what happens in these two cases. So the first example that I will have is say y at t is e x of t. Okay, now if the input is delayed by delta seconds, so I will have e x t minus delta. This will also directly go to y t minus delta. Like it's kind of this input delayed will give me this output delayed, and if the output by itself is delayed by delta, I will get this as also e power x t minus delta, right. So the output of t minus delta is just this computed at t minus delta. So this is one thing, and the second example I have is y equal to t times x of t. Sometimes it is easier to understand with examples which do not satisfy this, which actually are time varying. Okay, so now take the output delayed by delta seconds. This is my output t. The output y, the delayed output y t minus delta is how do I write it mathematically, is y at t equal to t minus delta. Again, x is the input, y is the output. So y at t minus delta, by substituting t equal to t minus delta, will be t minus delta x of t minus delta. Okay, this is the delayed output. Or the signal that you will see in this picture over here. Okay, now what happens to the same system? Now when I first delay the input, okay, now the input becomes x t minus delta, the output is generated by x t minus delta multiplying, okay, I am only dealing the input now. The input and output are related by this t x t minus delta, nothing happens here. This will be y dash of t. This is the output when the input is delayed by delta. Now for the system to be time invariant, this must be equal to this, and you see this is not equal to this, and therefore the system is time varying. Okay, so and this can be easily seem to be as time invariant. Okay, back to where we were, right? So this is time invariant, and this is time varying. How do I check mathematically? Is with these explanations here. Okay, nice. So far so good. So in conclusion, the output of a system, if the output of a system is independent of the time at which the input is applied, then the system is time invariant. So mathematically, if y of t gives me x of t, y of t minus delta should be equal to f x t minus delta. Simple example is maybe a resistor which does not change value with time, it just the R is constant throughout. In contrast, time varying systems, the output depends on the time at which the input is applied. Say, or mathematically it would mean that this does not imply the quantity on the right hand side. If I just take an aircraft and I say F equal to ma, as the fuel is being consumed over say a 10, 12, 14 hour flight, the mass tends to decrease, and therefore your m will be different when the flight is just about to take off till when it is just about to land. Okay, so we have multiple concepts now to ask ourselves question on. Just check, is the time varying system of the previous slide, which is y of t equal to 2t times x of t. I mean, is this linear? Can a time varying system be linear? Can a time varying system be non-linear, and so on? That's a good thing to check. You can also check if it is static or dynamic. Okay, that's kind of maybe a little easy to do. The last kind of systems that we will discuss here, of course, we will not spend much time discussing much time on that in this course, is the causal versus non-causal. In causal system, the output is depending only on the inputs that are already received, present or past. If I switch on a fan, then only it starts moving. If I switch on a light, only then it glows. My light doesn't glow thinking that I will switch it on tomorrow, and so it doesn't really depend on what will happen in the future. So these are also called systems which are non-anticipatory, right? Most systems that we look around as physical systems, thermostat, motors, generators, everything could be classified as systems which are causal. What are non-causal? The output depends on future inputs. System anticipates the future inputs and based on the past. A good example would be of all these energy distribution companies. Say, if you are in Mumbai, maybe you buy power from Tata or Adani or Reliance or whatever. The distribution company has to tell the supplier of how much energy they will need tomorrow, or how much the consumers are expected to consume in the next day. This is also called as a day ahead market. And they have some models which they predict how much the consumption would be tomorrow. This could be depending on the, if it's a Sunday or a weekday, if it's a rainy day, if it's a non-rainy day, if it's a full sunny day or a cloudy day, and so on. And based on some previous patterns, if it's a festive day, non-festive day, if there's a cricket match or no cricket match, they arrive at some models and say, okay, based on all these conditions, my future demand will be so much. Okay, so these systems anticipate future inputs based on the past. Okay, and also say if you think of say arrangements of now there's this Kumbh Mela going on a regular day, you don't people just come and go, right? There will be some kind of fixed amount of tourists which come, and therefore you don't need to possibly make special arrangements. Now maybe 1 million people will turn up each day starting maybe middle or end of January. You have to make arrangements accordingly, right? So your current actions, your things of what you prepare also depend on the future inputs. And other examples which we will which are under this non-causal are about weather forecasting systems, missile guidance systems, and so on. Of course, the focus will be much less on these things, but it is good to know where we are in terms of understanding our systems. So in much of our cases, we will focus on, of course, both static versus dynamic. We'll focus on systems which are linear, which are time invariant, and also causal. So this course will leave out a bit of non-linear. What we will do with non-linear is to convert them in a smart way to a linear system and analyze. We will not look in detail at time varying systems. Of course, we will also not much look about non-causal behavior, except in one instance of a control action where we see a bit of a non-causal behavior, but much of it we will look at linear time invariant systems, and the static versus dynamic and the causal will kind of be hidden in that. So much of this course will be on linear time invariant systems, also referred to as L, T and I systems. Okay, so in the next lecture we will just work out a little examples and look at models of systems that we see around us from different different domains from physical domains of say mechanical engineering, electrical engineering, also something which we see, which we would observe in the nature around us. So that's coming up soon. Stay tuned. Thanks for listening.